so this is essentially a consortium. The consortium involves contributors from IISc, IIT Bombay, IIT Hyderabad, IIT Madras, CDAC Pune, and Savitribai Phule Pune University. Okay, and this project is funded by National Supercomputing Mission. This is one of the projects funded by co-funded by DST, where you essentially the projects involve development of softwares, high performance computing tools, development of those tools, as well as application of very large scale simulations. So ours falls into the category of the development of tools, and that's what we are going to present today. So let's go ahead. Before we get started, I want to mention the team of contributors and members. So the team members involve Tanmay Datta, who is a PhD student, postdoc with me, Ajay Sagar. So a special thanks to Ajay Sagar. He is not available here. He had to go for a surgery, but he is one of the principal developers of what you will be seeing today. Dasari Mohan, he works with in IIT Bombay with Guru. Saurav Shenoy from IIT Hyderabad. Swarup Sampad he works with in IIT Madras with Professor Fani Kumar. Ankush Deshmukh and Abhishek Kumbhar work with Vaishali from Savitribai Phule University, and Abhishek Kaloke and Nasir Attar, who is not mentioned here, who are working with Venkatesh Shenoy in CDAC Pune. Apart from this, there are contributors: Swapnil Bhure, who is a PhD student of mine, Sangeeta Paul, who is also a project assistant, Adityan, who is a BS student, Bikramjit, who has passed out already. He was a past BS student with me, Ravi Kumar, who was a MTech student, and Jitendra Paraj, who is presently doing one of his bachelor thesis. So you'll see contributions from all of these people in what I'm going to show today. Okay, so the purpose of this workshop is to introduce you to MicroSim, as I just said, and to the broader materials modeling community. We'll showcase its capabilities and future developments that we. So it has 4 different modules, as you will see, and we will essentially detail the capability of these modules. We'll be concentrating on 3 modules in this particular workshop because the 4 modules were covered in the last one. We'll be showing updates in the software, which are principally in the 3 modules that we will be concentrating on today. Okay, so a brief overview why we are going through all of this exercise, and this is a good picture to start off with. It is essentially telling you that materials phenomena spans large breadth of length and time scales, and therefore, in principle, if you want to understand materials phenomena at any of these scales, you typically require, first of all, characterization tools to go and probe into each of these phenomena at these specific scales. But not only that, once you have an understanding, you want to do some modeling at these scales, you also, because of the disparate nature of the length and the time scales, you will also need different modeling techniques, and these modeling techniques are therefore are obviously scale sensitive. That means you have different modeling techniques at the electronic scale, and then you go to defects with the atomic, where you take care of the atomic defects and so on, and going all the way up to macroscopic, where you don't worry about atoms anymore. But if you want to have an holistic idea, you essentially need a scale bridging approach of all of these scales. And what we are going to be filling in here is essentially this mesoscopic scale over here, which is essentially somewhere in between this and this, where phase field comes in. Okay, so this is another map showing you the different models at each of the scales. So you see this green thing over here, which is at the mesoscopic scale, and that's one of the voids that we are going to fill in terms of the modeling capability. The reason I tell it's a void is because of the availability of software tools at different length and time scales. If you look at the macroscopic scale simulations, you have several of these tools available. Some of them are listed over here. If you look at electronic structure simulations, you again have a bunch of tools. If you have molecular dynamics tool simulation, you have again LAMPS and several others. Whereas mesoscopic simulations, particularly to do with phase field, which deal with the phase field technique, you will see that there are some of them, and there are restrictions on their usage. For example, some of them are commercial, some of them have restrictions on the type of model they use or the discretization they use, and that makes it prohibitive to a person who wants to venture and do some simulations with phase field. Okay, so that is one of the gaps we want to address as development of this MicroSim software. Okay, so our aim, why phase field? This is something important for people who are new to it. Phase field essentially allows you to understand things that are happening at the mesoscopic scale quite nicely, because it allows you to do something called modeling. It allows you to model microstructure evolution, which is essentially the question that you are addressing at the mesoscopic scale. Okay, so this method is particularly suited for such geometrically complex interfacial evolution, and therefore it's one of the method of choice for most of these problems. And one of the advantages of this phase field technique is that it gives you easy generalization for multi-phase. So if you write a code for a single 1D simulation, the formulations are generic, even in not only in the formulation wise, it's also in the code implementation wise, that it's easily extendable to a multi-phase, multi-dimensional situation. So that is what differentiates it from typically sharp interface models, which require computationally intensive strategies as you go from 1D, 2D, and 3D. Okay, so this is what is one of the pullers of phase field. I mean, why it's attractive as a method for this particular scale. So a brief overview of what we are trying to do with the phase field method. So a basic phase field method essentially looks like this, where you start from a functional, and you have the functional has different terms. Typically, you have terms which are controlling the gradient energy and the potential. So these two terms control the structure of the interface at leading order. Essentially, it means that it controls the interfacial energy of the system, which is one of the principal parameters that phase field automatically takes in implicitly. Okay, and then you want to move this interface with a particular driving force, and that's what is described over here. Okay, so this is what the basic phase field model is, and the reason just to give more supporting information for you why phase field is attractive. I'll give you some demonstration simulations over the range of phenomena this can address. So for example, this is a three-phase eutectic solidification, directional solidification, where we are trying to understand pattern formation. The bottom one is a simulation of coarsening in a superalloy, where you see coarsening happening. The simulation over here shows you electromigration driven grain growth and motion, which is also captured very nicely, as you see. And there are simulations of realistic alloys. For example, this is aluminum, zinc, magnesium alloy solidification. And these are ferroelastic domain simulations. And you also have the possibility to model crack propagation in these systems. So, so you see what you are not only modeling phase transformations, you are modeling interfacial motion due to other stimuli like electromigration, which is the electric current. You are also doing physics calculations which are to do with domain formation in magnetic and ferroelectric materials, as well as you are doing defect evolution during crack due to cracks and so on. So you see the wide applicability of things that happen at the mesoscopic scale and where the interface moves. So that's one of the reasons why phase field is attractive. Okay, so what is MicroSim? MicroSim is going to be, or is a software stack which is containing different discretization possibilities. So you have possibilities to do have codes and Fourier transform, FFT, FFTW, CUFFT. You have finite difference possibilities and finite volume possibilities. So there is a range of discretization possibilities. You have the possibilities to choose codes which run on different hardware. So you have the possibility to run things on CPUs and GPUs, all right? Which is one of the things the mandate of NSM is, because if you have looked at any of these supercomputing machines, they have a large number of CPUs as well as a large number of GPUs. Okay, so most of the time you will have situations where, let's say, some of the resources are occupied, but some other resources are free, right? Let's say CPUs are occupied and GPUs are free. So you will need a flexibility to where your softwares can run on both systems. Okay, and this is one thing we address in this particular stack. One of the other possibilities and one of the things that we have addressed in this MicroSim effort is that we have given the flexibility to modify models as you please. So what it does mean is we are not dogmatic about our models. We say that we give you a choice. You can also modify these models if you are a slightly advanced developer, but at the onset we also already give you a lot of choices in the modeling capability. And we will be we have already launched modules on solidification and precipitation, and there will be continuing modules on grain growth and recrystallization. And this is also what you will be seeing in the talk today. And just to mention, this is one of the first kind of its effort, which allows you to do high performance computing using both CPUs and GPUs, allowing the flexibility with discretization. So this is again what we have just said. Just to give you an idea of the state of the art with respect to phase field models, there are existing and ongoing projects with MOOS, Prisms, PF, HyPerc, OpenPhase, MMSP, Valberla. Most of them have a limitation. They are either accessible only on the CPU or the GPU. Okay, and there is a serious other limitation which comes in because most of them are written either in FEM, and there is no choice of the discretization. So that's one of the limitations we have tried to address. The other limitation with phase field models, for example, with MicroSim and PACE3D, they are prohibitively expensive, and they are not meant, therefore it becomes difficult to use them for academic purposes. Okay, so this is some of the things that we want to address in this particular project. So this is how the project implementation flow chart is. So we'll have we'll have modules. As I said, there will be 4 different modules, and each of these modules will be addressed using different strategies. So you have finite different strategies using explicit time stepping, using MPI parallelization. We'll also have explicit time stepping and GPU and CUDA and OpenCL implementations, as well as implicit solvers using Ambrex libraries, which allows you to have, with the same code, the possibility to run both CPU and GPU. Then we have Fourier spectral solvers, where are semi-implicit discretizations on the GPU using the CUDA FFT libraries. And we also have a CPU implementation for using the F50W OpenMP parallelization. Apart from this, we have OpenFoam multiphysics solvers, which allow you finite volume discretization, which will be allowing you to do which are parallelized on the CPUs using MPI. The idea is to develop all of these. Some of them we'll see today, and we'll present benchmark problems and scaling analysis on all of the strategies. A bunch of post-processing tools also, as you will see today, are launched. We already have ongoing documentation as it is on the repository, and we'll have regular releases of the software as you are going ahead. Okay. So the phase field models that we will be having in this particular module are the 3 major types. We have the grand potential model, which is going to be provided on CPU serial and CPU MPI as with CPU serial and CPU MPI strategies. This is based on this paper over here. You can all go and look at it. Then we have Kim Suzuki model, which will be implemented on the OpenCL and CUFFT, which also is based on this paper. And we have the Kahn-Hilliard model, which is the classic paper from Kahn and Hilliard. These solvers will have the capability with talking to databases, and this is the major update from the last release. You will see that the solvers are able to seamlessly talk with or implement information from the databases such that you can model real alloys. Okay. Okay, so this is essentially how so there are 2 classes of softwares. The solvers which are homegrown in some sense, which are written which are existing in our group, and there are multiphysics solvers, which means you use multiphysics modules solvers and implement phase field modules in those multiphysics solvers. So the homegrown solvers are phase field solvers, which means they will do only phase field, but it's essentially we are promising that it will do all possibilities that a phase field model can do. The multiphysics solvers essentially allow you to do many other things. Phase field is one of them. Okay, so we code in a phase field module inside a multiphysics module, which is OpenFoam and Ambrex. Okay, so each of the homegrown solvers are integrated in this fashion. You have the different modules. They are integrated using what is known as a MicroSim in-file generator, the thing that you will be seeing today in the lab, in the lecture today. The typical workflow of how you go about this is I'll also demonstrate to you, so you don't need to memorize this. It's essentially that you input, you have an in-file generator which takes in materials and simulation parameters. It also takes in the filling information, and you essentially compile the code, and which then gets executed, and you integrate and output files and visualize and post-process using the same tool. So a brief demo. Before the brief demo, as I will reiterate, one of the salient features of this particular exercise is that we give you a set of codes which you can easily run, but what you also get out of it is that you can build up. Let's say you do not like some part of the equations that you want to plug in something different, the software gives you the opportunity to do that in a very efficient manner, in that you don't have to write all the parts of the code, just the particular part you want to modify. Okay, so that is one of the modular nature of our code, which allows this easy incorporation or coupling with any model modification that you wish to have. Okay. Okay, I will give, this is a slightly older video, but it goes through the demonstration of how you launch MicroSim. It's just a video. I'll go through it's a silent video, but my video I will speak and go through the details of this as it's going on. Okay, so I'll play it. So the installation happens like this, where a MicroSim folder gets copied from the repository, and you will have different installation files for the different OSs, and you will have a MicroSim standalone folder which just has a Python file. Okay, so you can open this terminal and you can launch this Python file just as this, and it'll generate this front end is a bit old. We'll see the new front end in a few moments. But you can also do a system install, but just by choosing your OS like this, we have Windows installation as well. So if you just go here and you run the install.sh script file, it will essentially install it on your computer. All right, and you will have this installed. So once this gets installed, this is there in your home folder where he is navigating here. So it's there on your home folder, which has the bin where all your solvers will be. So you don't need to worry about this. This automatically gets handled inside the installation. And once it gets installed, you will get a logo over here where you can just click and MicroSim will be getting launched. Okay, so it'll launch over here. So one of the things that you can do with this is you can generate a new infile, or you can import an existing infile if you have one. So you can generate infile. The infile has different information. I will go through them in detail as we will go along. You can choose the infile. First, you need to choose a model, and then you basically navigate to an infile. If you do not have a original infile, you can start alone. He is just showing you what is being shown here is an import of an existing infile where all the important parameters get ported in. So you have so one of the things that you see here is these question marks at the sides of the keys. So if you go on the question marks, you will be able to see what those keys are and how what needs to be done for them, and you can fill them. So they host bunch of material parameters which you can fill in. You can fill in boundary conditions for the different fields that you're going to solve for, and that's how it goes. And then you can do domain filling. Okay, so you can fill domains with different shapes, and you can give the geometry of what shape you want to fill in, or you can import it from your original file or some file that you have already generated. There's a filling.in file, so it generates. You can choose it, and you can also edit that file from the keys that are there below. Okay. And similarly, you can choose the other models. The same workflow goes. Then you go and select a model and essentially put in model specific parameters. So the parameters that you just now saw are global parameters. Then you can go ahead and put in specific to the model that you're choosing, what are the parameters that you need to choose, and their documentation is existing in the manual. I will be also describing them as we go along. This is just a demonstration. And that's it. You will create these infiles, and once you have created these infiles, you can actually run them in the same console. So you can select run, and it starts to run on the thing. Okay. So okay, I think so. Once the run is over, I think it will go to 0.8 or so. Just a few minutes. And then once it's forward, you can close this terminal and you can preview the same thing in ParaView. The files are written in the same folder, in the data folder. To view them, you can actually go into the here itself and just preview in ParaView. Okay. And this will open, and so there's slightly different from the present front end. I will be showing you what it is, but essentially the same feature is what we are having here. Okay. All right. So let's go ahead. So what are the updates from the previous release? This is essentially for people who are already doing the attending second time. So we presented we have an addition of post-processing tools, as you will be seeing, thermodynamic coupling with databases, OpenFoam solver modules for multi-grain solidification, and the way we do this is through an orientation field phase field model. Then we have the multi-phase, multi-component extensions to the KKS CUA50 solvers. So the grand potential solvers were already multi-phase, multi-component. The KKS CUA50 solvers are also now multi-phase, multi-component. Then I have also changed the default of the grand potential solver to MPI instead of the serial code that allows you to use all the processors that are existing in your laptop. Also, there is in-file generator trimming. That means there were several keys which were sort of overlapping between the different solver modules. So they have been merged such that the number of keys have reduced, and some essential bug fixes. In addition, our repo, if you were to look at it, you can find them here. You can just copy this on your laptops and you can go to the repo where you will find the most recent software updates on this site here. We also have a website which is over here. Which is like this. If I were to navigate to this is nice. You can have a look. I will navigate quickly. Okay. Internet seems to be a bit slow. Okay, no, it's not slow. So. Okay, we'll see if it goes. Okay. Okay, so you go here and you will get a repo. You can click here and you will be able to go to our website, which allows you to show all, will be listing out all the details and downloads that you will be able to have for our software. So you can go through some of these things over here and you'll get much more information about why MicroSim and all of that. Okay. So that's for you to navigate. Apart from that, we also have a YouTube channel, which you can navigate from the website. And all the videos that we are having over here in the past workshop are already there. You will also have recordings of them of the same over here. Okay. Okay. Before we go here, I also want to give you a brief snapshot of what the post-processing tool looks like, or the new front end looks like. So I will just launch it here so that you all can see. So there's the new front end. And so I just wanted to give you a brief overview of what the post-processing tool looks like. So just let me do that. You need to go and look up the in file. So for example, this one. And then you need to import the VTK files. The VTK files are somewhere here. Okay, wait, let me go in. So, okay, let me choose them. So the loading depends on the speed. So you can follow what is getting loaded in the count that is coming over here. So here is the loading of the files. So there are 80 files. It'll just take about a minute to load them. Oh, sorry, I loaded the wrong one. So wait. Oh, wait. Let's close this. Come on. Okay. Well, let me just cancel this. This is going to take time. I'll have to just choose a different one, which takes a slightly lesser time. Sorry for that. Let's go to so this one, and okay. So well, it depends on whether I want to show you a precipitation or thing. So this is already loaded. So what you can do over here are several things. So first is you can already view how the microstructure is evolving like this. And then you can do several other things. For example, you can do front velocity calculation. So let's say I want to calculate velocity. I can specify along what line I want to specify the velocity, because it is a two-dimensional structure where velocity is not uniform. So one can choose a line. So I'm choosing a diagonal line which is crossing the tip of the thing, and I can immediately evaluate what the velocity is. You can actually play it. The velocity will evolve, and you can follow the velocity evolution as the simulation is going on. So let it finish. One can also do different things. For example, tip radius. So this is again the same thing. You can do the tip radius evolution and follow it as it is growing. So pop, and goes ahead. And in addition, you can plot other fields. So for example, composition is something that people are typically interested in. You can actually go ahead and do a plot over line. And you can plot how the plot over line looks like, which is the composition field. So several other things can be done. I'm just giving you a brief overview of what you can actually do with the simulation. And most of these you can just plot edit axes as you want. You can also write them to figures as in the format you want. You can output the CSV file and save it and then do whatever you want with the CSV file and several other things. OK, so this is sort of most things that a phase field simulation guy would do. One would generate the data and then do all that stuff. And then you can either close this and continue with a different post processing, or you can return to the original thing and continue with a different in file. OK, so that's what the recent front end looks like with the new release, and you can follow all of that. So I'll just show you just simulations, example simulations that have been done with MicroSim. So I will gradually develop into things that are complex. So naturally, one can do simple things like single dendrite simulations like this, where you can generate this. You can do multi-phase dendrites, which means each of these phases are having different orientations. So one is having an orientation which grows in orientation which is this way, and the other which is rotated 45. And this is not just limited to two. You can give any number of phases with independent orientations that are given, and then they will grow independently. Okay. So that's one of the capabilities that exist with us. So I will let it finish. So what you're seeing is the chemical potential plot as the things are growing. Okay. Okay, the movie is long enough. Oh, come on. Okay, then you can do multi-phase. So that's a single phase solidification. Then you can do multi-phase solidifications. For example, this is a binary eutectic, which is two phase, two component, but two distinct chemical phases, which is in contrast to the previous one, where the two dendrites have the same physical nature, but they are just differing in orientations. But these phases are different physically, and they're growing along in a coupled fashion. So they're chemically different, physically different as well. That also can be done. Similarly, you can do three-phase, three-component multi-phase eutectics, which are showing over here. Okay. Okay, so that essentially gives you, now these are all what was there in the previous release and what we have already shown as one of the capabilities for our software. And these are with model alloys. Now the transition is now to incorporate thermodynamic information and make it so that you can model real alloys. Okay. So I'll show you some more simulations with the model alloys. So these are precipitation simulations, for example, 3D precipitation simulations in 2D and 3D. And the 2D simulations also show you essentially the rafting of the precipitates. So the elongation of the precipitates in a particular direction, that happens because of the influence of elasticity. One particular component of MicroSim, which is quite attractive, is that you can use a large number of CPUs for doing your computations. So it's scalable. What I mean by that is we were one of the guys to test the Padam Praviga machine when it just came. So we got the opportunity to test scalability on a large number of CPUs. So what you see on the left and the right are two such simulations. So this 2000 cross 2000 simulation with 2 phases and 2 components was launched on 4761 CPUs. So this took about 3 hours 30 minutes. So it had 3 lakhs for 30 lakh iterations. Okay, 30 lakh iterations is pretty large for typical computations of the solidification type of 2-phase field computations. Now contrast this against 4000 cross 4000. So we have increased the domain size 4 times, but we have also increased the number of CPUs 4 times, and the hours, we still get the 30 lakh iterations in 3 hours. So that shows you that our codes are scaling with essentially the number of CPUs. Okay. These are some interesting other simulations that one can do. For example, these are done with 14,400 CPUs. And this is a directional solidification of a 2-grain microstructure. And so what you have is one of these grains are tilted with respect to the temperature gradient. So these are directional solidification simulations. Previous ones were isothermal. So this is a directional simulation where you are imposing a temperature gradient and you are essentially translating the temperature gradient across, and you are doing the simulation in a shifting box, so that the length of the simulation remains the same. And so again, this is essentially showing you that we can launch on several thousands of CPUs and still gain scalability. Okay, so these are essentially the new simulations which I wanted to highlight to you for the guys who are attending for the second time, which is the coupling with databases. And so these simulations that you see over here, for example, this is a simulation of the aluminium zinc dendrite. So this is a aluminium dendrite growing from the liquid, right? And these are done with coupling with databases. Okay, so what you see on the left is a single dendrite growing. Okay. And on the right, what you will see is a multigrain dendrite, which is growing, which is typical of a realistic microstructure where you have multiple grains and you have solidification happening. Right? So we'll just let this finish and then. Okay. So you have dendrite growth and then it goes into a coarsening, and you also see there are grain boundaries that are existing over here, which naturally come into the model. Okay. Okay, then you can do, these are binary simulations, but you can also do ternary simulations, again with coupling with databases. So this is the NIL-MO dendrite in a NIL-MO system, where I'm just plotting the aluminum and the moly concentrations. And so similar structures, I will just go quickly so that in the interest of time, where you are essentially seeing the same thing. And so this is so I've shown you binary, you have shown multi-component, and then you can also do multi-phase, as I showed before. In the there's a eutectic in the aluminum zinc system, so which also is accessible to us. So which is something that we are going to show here. So the first is the this is the phase plot, and this is the composition plot on the bottom. So this is again done with a feature of the model, which I highlighted in the previous workshop as well. There is a shift box integrator, which means that you shift the domain out of the simulation because what is happening behind is not interesting. So you shift uninteresting part of the simulation, such as the length of the box remain the same, and the simulation domain remains finite. So you see, I started with a different volume fraction. It goes to the correct volume fraction, and all with talking to the database. Okay. So coupling with databases is what we have demonstrated using the MicroSim Grand potential solvers. We also have multiphysics solver modules using the OpenFoam, and these are essentially meant for doing casting simulations. So if some guy is interested in doing, let's say, for some imposed cooling rate, what is this microstructure evolution? This can be done using the multiphysics solver module in OpenFoam. So some of these are shown over here. So this is using the orientation field model. So this is not multi-phase model, but this is an orientation field, as you will see over here. So this is the phase plot on the top, which is evolving. And this is at the bottom, the orientation field evolving. And as you are evolving, you are essentially cooling down. So your temperature is evolving. So you have cooling down, and then because of the growth, the temperature saturates because of the latent heat evolution, and then you start to cool because the growth rate starts to. So you essentially have a typical cooling curve that is there in experiments, which can be seen over here. So I will let this progress a little bit. So some of this you will also see in Tanmay's talk, a more elaborate development. So this particular module has been a development of two of Ajay, not Ajay, Swapnil and Tanmay. Swapnil is my PhD student, and Tanmay is a postdoc as part of this project, and you will see that. So I will just go ahead in time in the interest of thing. So you will see multi-grain solidification. So you can also do comparison with Scheil type calculations. So the red line over here is the Scheil, and what comes out, what you can extract from the phase field simulation in terms of CL versus FS. Okay, so this is a composition of the liquid as a function of the fraction liquid. So you're not able to see the axis below, so I'm just reading out the fraction liquid against the solid. So this is a module which you can directly use for typical casting simulations. This can be done both for ternary, a binary and ternary. So this is a NIL MO, for example. I'll just go to the final plot in the interest of time. Come on. And you can do similar stuff. And you can again extract the same type of information, temperature versus time, and you can also extract the cooling rate as a function of that the system sees. So the previous one is previous simulation that you saw. The cooling rates are more in the line of what you would experience in additive manufacturing simulations, additive manufacturing conditions, whereas this one is typical of what you would typical castings, where it's just slower in cooling rate. Okay. So this is our team of developers. This is slightly outdated, but the credits are already there before. We also have, I want to acknowledge previous contributions from my group, which have been PhD, master, and UG students. So for example, Sumit from my group, Tushar from Shashwata's group, Gerald, who was in Funny's group, Ravi, who was an MTech student, Bikramjit, a BSMS student here, and Umate Kartik. All have contributions which are already part of the codes that are already there in the repository. Okay. Okay, so with that, I actually would like to thank you. This is enough advertisement for what MicroSim is all about. And the following modules, you will essentially go through how to run each of these modules yourself. So we'll go through in a sort of partially hands-on, depending on what you can install on your computers. And you will see a live demonstration of several things that I've just shown here. Okay. So with that, I can take in questions if you have, and yes, there are people in the audience. Okay. Hello. Wait. So there's somebody from speaking. You can just unmute and ask your question. Anybody has?
Sir, this is Sriman. I wanted to ask, sir, why do we need so many?
They're speaking, but it's not passing on to the.
No, it should come.
Maybe I have to put in this one.
I think
no, Shriman is speaking. I think. Shriman, you can speak. Just tell your question.
Yes,
yeah.
Sir, my one basic question I have is like, why do we need so many phase field mode?
Just wait, just 1 second, Shriman. I will just change the device settings so that Shriman, can you repeat your question?
Yes, sir. Sir, my basic question is like, let's say we are solving for composition and the order parameter.
Yes.
Why do we need so many different sort of phase field models? Like, why can't we use one phase field model? Like, for example, if we want to study composition or order parameter variation, why can't it be just like grand potential model instead of KK? Like, for the same problem, KK also is being used. For the same problem, grand potential can also be used.
Okay,
Why?
so Shriman, this has to do with yes, we can do that. Okay, so that's no doubt. One can choose each of these models, and essentially you can have everything. It is a matter of choice that we have kept it as a stack. The reason for that is, and each stack is complete, by the way. So
Okay.
I mean, at least in the final situation, that is what we plan to be. The idea is the user can have varied interests, and that's what we perceive. So we can think that our model can do everything. It indeed can, but a particular user might think, okay, I may be having some contribution in a KKS model, which I would like to have and I want to like to use. All right. So it's a different perspective in the sense that there is an attachment quotient with a particular modeling strategy that some people might have. Okay, and we try to respect that. So and not be dogmatic about, okay, this is the solution we provide and this is what you need to use. We give a certain diversity and certain uh, things to certain possibility to choose between the models that are possible, and that's the way we have chosen to evolve. Okay, indeed we could have just chosen one of them and do, but in the interest of the diverse possibilities and also there is a physical thing also. So for example, in a grand potential model, I can in principle, you can make each of these modules sort of having the same physics, as I will show you in the modeling of in the next session, where it becomes irrelevant which model you use. You can actually get the same result. Okay. Again, so it boils down to whether somebody wants to keep calling that I use a KKS model, or somebody wants to say I want to use a grand potential model. Okay. So it's a matter of choice of the user, and we respect that. That's the whole point of doing this.
Okay. So one more question.
Yes.
Last time also I asked this thing, like multi-grain models, like initial grain structure models. Is there any plan to include that also?
So multi-grain solidification is already part of the multi-grain solidification is already part of the OpenFoam solver modules as well as the grand potential model. So you can already do that. So you can already get segregation as a function of diffraction solid and all of that. All right. The thing that we will be doing in the next release is grain growth. It's already there, but it's not optimized. So you can already do grain growth simulations. That means you can start with 20 order parameters in the in the grand potential model, and you will get grain growth, for example. But we would like to optimize it in a manner that so that it runs most efficiently. Yeah, that's the only point.
Okay, sir.
So the next release is the aim is the grain growth and the elasticity incorporation in all models. That's it.
Okay, sir.
Okay, there is somebody raising their hand. Yeah, Subbarayalu, yes, that's what I showed. If I can read Subbarayalu's question. Can we simulate solidification structure and curve at cooling rates experienced in additive manufacturing conditions? So that's what his question is. Yes, that is what I have shown in this simulation. So for example, let me just go back. So if you were to look at the cooling rates, we have not plotted the cooling rate over here, but if you were to evaluate the cooling rate over here, you actually have 10 power 5 Kelvin per second. So the microstructure over here that we are simulating is what would be relevant for an additive manufacturing simulation. So the cooling rate is something that we can handle by choosing the input parameters in the OpenFoam module appropriately. Similarly, you can also do typical casting calculations, which is what I wanted to demonstrate over here, where the cooling conditions are what you would find in a typical casting simulation. Yeah. So. So, Badayalu, does that answer your question? Okay. Isha Kumar has a question. Can we also model divorced or partially divorced eutectic microstructure? Yes, you can do. The thing is about divorced eutectic, you don't nucleate them together. Well, the nucleation is in any way one of the things that we do not handle in a phase field model. So divorced eutectic is something that we can model. There's not an issue. This is part of the Grand growth GP formulation. So the MicroSim GP formulation can already handle all of this divorced eutectic stuff. Isha, Ish Kumar, sorry, not Isha. Ish Kumar, does that answer your question? Okay, all right.
Hi, sir. This is Akash.
Yes, Akash. Yeah, go ahead.
So you have said that you have done some simulations for very high cooling rates.
Yes, yes.
So just wanted to know what is how are you incorporating the non-equilibrium thermodynamics for the?
So that's not there in the model as yet, but it can be incorporated. Okay.
Okay.
So by modulating the anti-trapping current. So remember, if you incorporate the anti-trapping current in its totality, you will not have any non-equilibrium stuff. Okay. But naturally, in a phase field model, if you leave it by itself, you will automatically have some trapping.
Okay.
Okay. So the question is to modulate the trapping to get to the experimental condition.
Okay.
And this they can be done.
Okay.
Okay. So this is something that we might release maybe in the as one of the sub releases of this release. Okay.
Okay. Sure.
Questions? Questions from the audience, maybe? Okay, so if that's not the case, what we will follow up now is essentially now is the installation session, right? Yeah. So both the online and the physical participants of my students will help you along in installing the MicroSim required installation files of MicroSim so that you have them on your computer and you can play along with me when I am demonstrating stuff. All right. So that's what is the idea for the next part of the session here.